Alright, hello and welcome to all to the last lecture of the chapter Light. Today we are going to discuss regarding the phenomena of atmospheric refraction. Right, atmospheric refraction, the topics which we are supposed to be covering today is basically, this is the last lecture list. That's lecture 5 of Human Eye in the Colorful World, and the topic which we are going to cover over here, the first one is the concept of atmospheric refraction, and the second topic is the concept of scattering of light. Both of these phenomena can be seen. I mean, it's like a very natural phenomenon, right? In the previous sessions, we have already discussed regarding the various prism concepts of prism and how light disperses into 7 bands of colors, right? So here I have a prism of some angle and a white light entering into the prism, getting divided into bands of 7 colors. True. Similarly, today we are going to talk about the concept of atmospheric refraction. It's one of those very, major and very interesting topics. What will be your reaction if I'll tell you that the sun which we see in the morning, we are already 4 minutes late. Point is कि हमको जब सन दिखता है ना, तो उस समय तक तो सनराइज हुआ भी नहीं होता है. सनराइज तो 4 मिनट बाद होते हैं. Similarly, the sunsets also which we see is also a delay of 4 minutes. That means in this whole phenomena, there's a early and a delay pattern which is being followed, or the twinkling of the stars, right? Why all these things happens? We have already talked about the concept of refraction, right? And we know over here that path changes due to change in medium. So in a medium, if say there's a light which is trying to enter from one medium, say mu1, into another medium mu2, and it's like the denser medium, so obviously it has to bend towards the normal. Some kind of phenomena like this is also seen in the case of atmosphere. Like for example, there are 2 factors which plays a role. Temperature plays a role in the concepts of density. Higher density, lower density, we can have the concept, right? This is like the say lower density, this is the high density. True. The factor which plays a role over here is temperature. How? We should have the concept that temperature is inversely proportional to density. That means if I increase the temperature, the density will decrease. If I decrease the temperature, the density will increase. Like for example, you just try to consider yourself that I have kept you in a room, right? And the temperature of the room is very high, like for example 50-55 degrees Celsius. Will you be sitting comfortably over there? No, right? I mean, you will be jumping from one position to another position to the third position, keep changing your positions, right? That's what you will be keep doing so, just to make yourself a bit cozy. In the other case, if I decrease the temperature, like for example, I decrease the temperature to 0, 1 or 2 degrees Celsius, you won't be jumping around, right? I mean, you will be sitting at one corner trying to warm yourself. Similarly, if I increase the temperature, will the molecules be quiet? No. Even they will vibrate. And due to their vibration, the distance between the molecules will increase. And hence the density will decrease. So density could be considered in a kind of relation with the temperature. So if I increase the temperature, density decreases, or if I decrease the temperature, density increases. True? Now, let's say if here, change the color, yes. So here we have a sun, right? Here we have a sun. This was a ray of light going. As soon as it entered the atmosphere, due to change in temperature, due to change in the density. There are various factors which plays its role. It keeps deviating, deviating, and then it finally reaches to us. Right? That means, as you can see, there are multiple layers, right? As you can see over here, there are multiple layers. There's a layer over here. There's a layer over here. There's a layer over here. So at all these multiple layers, will there be refraction? Yes, absolutely. See here, a ray of light, then getting refracted, then getting refracted again, then again getting refracted. That means at every layer there's a refraction taking place. I can say that at every layer, refraction is taking place. Refraction is taking place. Right? Every layer this phenomena is happening. Right? And so we see the sun, although it's not up to our level. But you know what? Our brain perceives that, oh, the sun is straight away. The brain is not capable of understanding the phenomena of refraction. So it thinks that the sun, this is the path of the ray of light followed by the sun. That's what the brain thinks. And so this is the perceived positions, as you can see. Perceived position. And basically, is this the true position? Is this the real position? No. It's just an image which has been formed due to multiple refractions. But this is the true position. So the concept of atmospheric refraction could be understood in a way, and also you should note a point over here that in morning we see the sun, we see the sun 4 minutes earlier. We see the sun 4 minutes earlier. The sunrise. So before the sun rises, we are already seeing the sun in front of us. Similarly, in the evening time, at sunset, we see the sun. 4 minutes even after sunset. Even after sunset. So the point when we go to particular points at hill station, there are like tourist destination, sunset point, sunrise point. Basically, the sun which we are looking at has already settled down, but still we feel that, oh, that's the sun settling down. But the point is, it's just a virtual image of the sun. Actually, the sun has already settled down. You getting this? This is the phenomenon of atmospheric refraction. Similarly, as you can see over here, here we are talking about the concept of atmospheric refraction due to the concept of temperature. Due to change in temperature, we are talking about this, as you can see. See, here it's the cold air, here it's the warm air. Here is an object. Now this ray of light was supposed to travel straight, correct? See, this is a ray of light and it was supposed to travel all the way like this. All the way like this. But it did not. Why? Because of the change in density, cold air and warm air. And due to the change in density, the ray basically bends like this, and then it's perceived by our eyes. Then it's perceived by our eyes. And again, as I said, like just in the case of the sun, that's a perceived position. Our brain perceives the object to be like this. And this phenomena is very much observed in desert regions. Desert region. And it's called as the mirage. Why? Because you just try to understand that here we have a desert over here. And the air just above the desert will be warm. And as you keep rising, the level of the temperature of the deserts will keep on decreasing. Will there be a change in density? Yes, absolutely. Due to change in temperature, there will be a change in density. and thus we see a mirage in various locations. In desert, you can obviously see that. And many travelers, those who are like traveling in the desert, they feel like, oh, there's an oasis being formed over there. But actually, there's no oasis. Why there's no oasis? Because it's a kind of mirage again. Are you getting this? Probably. Sure. The next phenomena is the phenomena of scattering of light. To make you understand the phenomena of scattering of light, let me explain you by giving you an example. Let's say that all right, I have a container like this, and I have another container like this, and it's completely a dark room. Just try to imagine that this is completely a dark room, and there are two containers filled with water. All right, they both are filled with water, and they are kept on a surface over here. They are kept on a surface. And here's a screen. You can see there's a screen over here, right? We have a screen over here. So as you can see, this is a surface and this is a screen, right? And I am taking a laser light, say a laser light of green in color, right? A green color laser light is used over here. This ray of light will be seen over here, then it won't be seen in this part. Or you can just say it as, you can just say that you will observe an image, the light over here. This laser light will be seen. Will it be seen in this whole path? No, it won't be seen neither in the glass, neither in the air. Both of them are filled with pure waters. Both of them. Now what I have done is I have mixed this with milk. I've mixed this with milk. Only for one of the container. Let's say I have mixed milk in container number 2. This is the second container, this is the first container, and next one milk. As soon as I mix some milk, you will see the ray of this laser light. This ray can be seen clearly. Why? Why the ray of light was made visible when the milk was added to it, and it was not made visible when there was no milk into it? This phenomena is called as the phenomena of scattering. And this phenomena is called as the phenomena of scattering of light. What scattering of light? Now, why is it so? Let's try to understand this. Now, say here this was a molecule, a milk molecule. And this was a ray of light. This was a ray of light. As soon as it strikes as soon as this ray of light strikes, this ray of light strikes this molecule, this molecule reflect, the phenomenon of reflection is taking place over here. It reflects this white light into almost all the angles, like this almost at 360 degree reflection is taking place, right? And due to this reflection, due to this phenomenon of reflection, this milk molecule will now start appearing as red color, red color, right? So there was a ray of light, this was, you can say, this ray of light striking a molecule, and the molecule then scattering this light into different angles, and ultimately representing this in the red color itself, or green color. For example, in this sense, we are taking a green laser color, so that's laser light, so that's why it's a green color. If it's if I'm taking a red colored laser light, then it will be obviously red in color, right? This phenomena is called as scattering of light. So scattering of light, as you can see over here, scattering of light is the phenomena in which light rays get deviated from its straight path. Light ray gets deviated from its straight path. See, straight path getting deviated on striking an obstacle like dust or gas molecule. I'm just taking the example of milk over here, but gas molecule can also be, or dust can also be used. Water vapors, etc. Scattering of light gives rise to many spectacular phenomena such as Tyndall effect and the red hues of sunrise and sunset. Now, what are these? I'll explain it. You must have seen in the forest regions. This is just try to understand it in a way that there's a very thick forest region over here. There's a very thick forest region, and the sun rays we can see sun rays coming out of it, right? Forest region, and there's a sun behind, and we can see from those small areas where there's no leaf, right? We can see light rays coming out of it. That phenomena is called as Tyndall effect. That phenomena is called as Tyndall effect, right? And why the second question is, so what the first question is, this is a kind of one of the common question, what's the scattering of light? I hope you must have understood this, that whenever a light particle strikes a molecule, it undergoes multiple reflection, which basically give rise to various phenomena such as Tyndall effect, the first one, and the sun red hues of sunrise and sunset. The second phenomena is this: why does sun during sunrise or sunset appears to be red? We just try to understand it in a way that from the previous slide itself could be explained that when the light is coming over here, right? Light is coming over here. It undergoes multiple refractions and it also undergoes dispersion. Yeah? So there, let's say there's a ray of light, and then it's getting deviated like this. At the last, we have which color? Red. So say it is like, let me redraw this in a better way. Say this is the earth, you know, and this is the sun. Say this is the sun over here. And it's near the horizon. So obviously it is almost about to set. Now, when the light will be coming out of it, light will be coming out of it. Say, yes, it's a ray of light coming. Then obviously it undergoes multiple diffraction, and then it deviates into it scatters into different colors, and it scatters into this color, and this color. Vibgyor, basically a vibgyor will be formed. Vibgor. Now, which is least scattered? Red. Red light. Red light is least scattered. Least scattered. So due to the least scattering of the red light, it basically deviates. The minimum deviation is basically taking place, right? The minimum deviation is taking place by the red light. Other lights are going above to us. And so we believe that red is the color of the sun whenever it is about to sunset. It's the time to sunset, right? Because red color reaches our eyes and rest of them are basically moved in the upward direction, which is way beyond our limitations, right? Am I clear till this part? So I think you must be clear now. After considering covering this topic, you should be able to understand the phenomenon of scattering of light, then Tyndall effect, and red color of the sunrise and sunset. Let's see. Which of the following phenomena contributes significantly to the reddish appearance of the sun at the sunrise or sunset? We just discussed it. It's not even dispersion, it's not scattering, it's not IR, and it's not reflection. Oh, sorry. It's scattering. Scattering of light is the reason for the reddish color of the sun. The splitting of light into its component color is called as, see, there are two phenomena: scattering and dispersion. In the phenomena of dispersion, this is basically performed by Prism, where a white light is basically deviated into 7 constituent colors. This is the phenomenon of dispersion. Whereas scattering is what? A ray of light striking with a molecule and getting deviated into different directions. So the splitting of light into its component color is called as dispersion. Don't get confused with this. So dispersion will be the correct answer. Clear? The stars appears to be twinkling because of, yes, this phenomena was left to be discussed. Just try to understand that why the stars appears to be twinkling. Say, here is the surface and you are standing over here. And here we have one of our star. This is the star, right? As sun is also a star. Now, this array of light, you know, this array of light coming, and then getting deviated, and being perceived by our eyes, you know. This array of light, ray of light, and then getting deviated. And so we believe that the star is basically in a straight path over here. This is the perceived position of star, and this is what's its real position. True. Now just try to think about when it is over here, is it going straight? No. If I zoom into over here, the path which is basically, say this is the surface, the path followed by this ray of light is like this. And so our eyes will perceive in all the directions. So eyes will believe that there's a ray of light coming from here, and then coming from here, and then from here. So there are multiple lines through which we perceive that there's a ray of light coming. But is the density or the temperature constant all across? No. The temperature and the density does varies, right? So say if the this is ray 1, this is ray 2, 3 and 4. If the density of the 3 has decreased, it will look like a bit dull, right? And point is that at one time the density of one of the rays will increase, at other time the density of the other ray will increase. So this constant change in the density of various rays ultimately results in twinkling appearance of the stars, right? So this is basically the phenomenon of change in density. Change in density or temperature, or even both can be the reason. Our sole purpose is just to make the light deviate. That's it. And yes, atmospheric refraction is the correct answer. Tyndall effect cannot be observed because it's due to the scattering of the white light. That's absolutely not true. The spectrum is never formed. Reflection is not the phenomenon, and obviously atmospheric refraction will be the correct answer, as you can see, right? So what we have studied over here is the concept of atmospheric refraction, the various phenomena related to it, like the concept of mirage, the perceived positions of the sun and the stars, and the twinkling phenomena of the stars, then scattering of the light, right? Then why a ray after striking to a particular molecule scatters at different angles. Then these are the various practice questions that we did practice. I hope this was clear to you. Bye bye.